Thank you for coming by and watching this video. If you enjoyed this video or feel you've benefited from it, consider going to patreon.com/newbiehack and support these efforts. You'll have access to 20 of my latest videos that hasn't been published on YouTube yet. So in our code, we can just take a look at this order of operations from a timing diagram, and we know that we have to, for the write cycle operation, we first have to make the change for the read-write to go into the write mode, which is low, and then change the register select to be in the correct mode, either in command mode or outputting a character mode. Then we have to wait 40 nanoseconds minimum. So in our code, we'll just have some kind of delay there. And then we can turn on the enable. Immediately after that, we can output the byte. And before we turn off the enable, we have to wait 80 nanoseconds. Then we have to wait a minimum of 10 nanoseconds to modify the data pins or bring the read-write high or change the RS if we have to do any of those things. And then before we do another cycle of writing or reading to the LCD, we have to wait a minimum of 400 nanoseconds, which actually brings us back up to this location here. We've already taken care of the code for outputting the byte. All we need to do is now take a look at doing the other operations around that. We can do all of this in the main.c file, which is our main code, and we can test it to see if it works. We can change the read-write and the register select, turn on the enable, and then output our byte, and then turn off the enable, and then wait for a certain amount of time after that to do anything else. So we'll hard code a time delay after all of that, so we don't do anything to the LCD. You might notice that there's a bit of time going on here where we're having to modify signals like the read-write, the register select, and then turn on the enable. We have to wait throughout the process, and the whole process takes about 500 nanoseconds. And it may not seem like that's much time, but we're still tying up the microcontroller during that operation, where you're using hard-coded delays. Everything I've seen on the internet uses hard-coded delays for writing to the LCD. I haven't seen anything where they're doing anything more sophisticated, like using interrupts to turn on certain signals for the LCD. But I'd like to take a look at that. I'd like to investigate using interrupts and timers later on in the ARM series, where we can actually turn the enable on and turn the enable off and specify how much actual nanoseconds between those. We'll probably go a little bit more of a length of time in nanoseconds, just so we make sure that we're not interfering with any processes with the LCD. But you can imagine when you're using the ARM microcontroller, the reason why you would design software in this way anyway, without using some kind of operating system like a Linux kernel or something, is that you want to really utilize the ARM microcontroller fully. You want to hook up sensors to it, some motors, maybe some servos, do all kinds of different things, and have many processes in a sort of a state machine running on the ARM microcontroller. If you can imagine like your car dashboard, if you have a dashboard that has a lot of digital readouts on it, maybe showing the speedometer in digital, you'll notice that a few seconds, or maybe a couple seconds, or maybe a second, it shows the speed change. It doesn't show instantaneous, like it's ramping up or ramping down. And there could be some reasons for that, but every single digital readout I see on my dashboard, it has time delays, and I'm thinking that the developers of that software may not be. They probably need more time for those microcontrollers for sensing more important systems in the engine, running the engine. mass airflow sensor or sensing the oxygen or whatever in the car, maybe sensing the fuel going into the injectors or whatever. Maybe they have some flow sensors, but those are more critical than looking at a dashboard of numbers. But if you have all that set up as timers and you have digital signals change with interrupts in connection with those timers, you're not tying up the microcontroller at all. I mean, with it would be an extremely small amount of time, and it would be an insignificant amount of time you're tying up the microcontroller. So you'll be able to have the access to the LCD. You'll be able to write to the LCD in real time and in a very fast and fluid way while you're listening to sensors and maybe outputting to other devices or something like that. So later on in the ARM series, I'll get into, when we get into timers, I'll get into looking at or investigating what it would take to use interrupts and the LCD. And this would be something probably brand new to the internet, because I haven't seen anything like this on the internet where they actually use interrupts and timers in connection with using the LCD or outputting the LCD. So the next step in this process is to, one, we could set up the LCD on the circuit, and then hopefully it will work and we'll get the enable, read, write, and register select connected to the LCD and sort of hope it works. But I'm inclined to add a few more LEDs and test the outputs and the order of operations. And I think this is a good way to understand the whole process. What I'll do is I'll set up 3 more LEDs on the breadboard, and we'll add some delays in between the operations as they happen. So we can see with the LEDs how those operations are happening, when the enable is turning on or turning off, or when the data pins are firing the particular byte, and when the read, write, and register select are turning on and off. But of course, we're going to have to make those timers, we're going to have to make those delays a lot longer, because we need to be able to see this kind of process happening. And then when we get to the final putting the LCD on there, all we have to do is remove the LEDs, put the LCD inside, put the contrast and voltages and stuff like that on there, and the LCD will test and see if it works. I plan on putting the LCD along this area here. The LCD has 16, 15, about 14 pins. I'm not sure if I have these actually as pins, but if I do, then I can just cut them off. Or I can just move some of the wires on the breadboard. On the breadboard I have, including these 2 LEDs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So I do have enough pins here. I made these wires pretty tight, so I may have to extend these so they come out, sort of do an L shape, so I can fit the LCD along here. Or I could take these wires for the ground and 3 volts. I can move those over a little bit, just in case these wires will get in the way. So that means that I'll definitely be using these 2 LEDs, and I'll probably change these LEDs to the, let's see, what's the next ones? We have VSS VDD and V0, which is the contrast. So we have the register select. So the register select could be the first one. The second one is the read write. So the read write would be the next LED. And then the enable would be the LED that's on this pin here. And then after that, we can have these pins from D0 to D7. We can have them along this side here. We'll just use some jumpers going to these tie strips. The next, let's see where they are. Yeah, here we go. the next pins, which is, we're using the pins number 33 through 40. And 33 is at this location of the breadboard, 33 and 34. So we'll need 3 more pins, and I think 41, 42, and 43 would be fine since they are also the 5-volt tolerant pins. And I already looked at the data sheet to see if there are any significant features that they would have, and they're not. So I'm going to go ahead and apply some LEDs to those pins, and then we can test the enable, read write, register select, and the byte again. So let's get started.